Good morning, students. You are welcome back from the short break. This course, Basic Enzymology, is going to be handled by Professor Kabiru, as myself, Dr. Famous Osamulu, and Mrs. Halima Saadia. The course is divided into two parts. We have vitamins and coenzymes, which will be handled by Halima Saadia, and then the aspect of basic concepts and kinetics of enzymes will be handled by myself, and Dr. Osamulu. I'm going to be the lead lecturer, and to begin, there are some basic questions we need to answer. And at the end of the whole course, students should be able to give answers to these questions. And we go like this. The first question is, what is an enzyme? You must have heard of the name enzyme in your basic biology at secondary school level. Then we want to know what are the characteristic features of enzymes. And thirdly, how do enzymes differ from ordinary chemical catalysts? Because we have organic and inorganic catalysts. How do they differ? And how do enzymes work? And how can enzymes be so specific to the point that enzymes will only act on substrates for which they are made? And what are those factors that affect enzyme activity? And how are enzymes classified? And then we need to know what are the basic or fundamental equations of enzyme kinetics. And we want to know whether enzymes can be expressed in a mathematical equation. Enzyme catalyzed reaction can be expressed in a mathematical equation. And what are the different types of inhibition of enzyme activity. This is the whole about the basic concepts of enzymes and how enzymes work. First, we start with what is an enzyme. Enzymes are central to every biochemical process in the living system. All reactions that take place in the living system are catalyzed by enzymes. And that is what gives the impetus for us to live. The moment enzymes stop working, the living system will die. And the definition of these enzymes is that they are biological catalysts that speed up biochemical reactions involving nutrient molecules in the living system. We take in food in the form of carbohydrates, lipids, fats. This food have to be acted upon by specific enzymes for us to get the benefit from the food we take. So carbohydrates have to be broken down into glucose. Proteins have to be broken down into amino acids. Fatty acids, lipids have to be broken down into fatty acids and glycerol. It is these end products of enzyme action that benefits the system. If you were to take carbohydrates without being digested, it will be useless in the living system. Also, enzymes conserve and transform chemical energy and make biological macromolecules from simple precursors. The end product of enzyme action is energy. The energy that will enable us to do work, the energy that transforms one form of biomolecule to another form of biomolecule, the synthesis of ATP, which is the energy currency of the living system. All these are catalyzed by enzymes. So the study of enzymes as biochemists and microbiologists has immense practical importance. In disease situation, especially in heritable genetic diseases, there may be a deficiency or even a total absence of one or more enzymes. As we go along, we get to know some examples of this. If you say someone is suffering from a particular disease, it's likely to be linked to the absence or inefficiency of that particular enzyme related to that disease. We have different disease conditions that may be caused by excessive activity. So when you have deficiency of activity or total absence or overactivity, this can lead to disease. And most enzymes in living systems are protein molecules. But there are very few RNA molecules that also act as enzymes in the living system. And what do enzymes do? Basically, they act on substrates to give rise to products. And these substrates, we call them reactants, while the products are what you get after the reaction of an enzyme. This is symbolically what you have as reaction between an enzyme and its substrate. It forms an enzyme substrate complex, And then this is broken down to give you your enzyme and products. Enzymes do not act alone in most cases. They require cofactors. Cofactors are the molecules that assist enzymes. They help enzymes to promote their optimal arrangement in terms of atomic structure and enhance proper functioning of the enzyme. These helpers are generally referred to as cofactors. And these cofactors are non-proteinous substances that associate with enzymes. And a cofactor is essentially necessary for the functioning of an enzyme. In its absence, the enzyme may not function. An enzyme without a cofactor is called an apoenzyme. When a cofactor comes together to make an active enzyme, it's known as holoenzyme. So an apoenzyme plus its cofactor is referred to as holoenzyme. We have three kinds of cofactors. We have those that are referred to as prosthetic groups. These are cofactors that are tightly bound to an enzyme at all times. They are embedded in the enzymes. And so the enzyme exists with them, and they are known as cofactors, and they are tightly bound. We have a second category. These are known as coenzyme. These are bound transiently. They only come into action with the enzyme when they are needed. And they come in the form, mostly in the form of vitamins. And that's why vitamins, when you come to define them, you say they are required in minute quantities for the sustenance of life. And a prominent example is nicotinamide adenosine dinucleotide, which is symbolized as NAD+. There are many enzymes like the dehydrogenases. They cannot act without NAD or FAD. So this category of cofactors are known as coenzymes. And the moment they act with the enzyme, at the end of the reaction, they dissociate back to their normal state. Then the third category are the metal ions. For some enzymes that are classified as metalloenzymes, they require a metal ion for them to be active because they form coordinates in the active site of the enzyme. We have examples like alcohol dehydrogenase that is involved in catalyzing alcohol into aldehyde. Those that take alcohol, this is the enzyme that metabolizes the alcohol. But this enzyme cannot act without the presence of zinc in its active site. Another example is carbonic anhydrase, which is an enzyme of the blood that also acts on hydrogen carbonic acid that transforms to water and carbon dioxide. It also requires zinc for it to be active. Then we have characteristics features of enzymes. Enzymes have very peculiar features that make them different from inorganic catalysts. They endure living systems with remarkable capacity to exert kinetic control over dynamic potentiality. Because we know enzymes act in the system to sustain life, because of that, they are amenable to changes. Depending on the needs of the cell, the enzyme could be active or inactive. There are a class of enzymes that will only be active when the substrate they act upon is in the system. Once that system or that substrate is not in the system, the enzymes remain inactive. Enzymes are agents of metabolic function. Metabolism is breaking down of the molecules you take in as food to give you byproducts in terms of monomers that the body can utilize. And I have mentioned glucose, amino acids, fatty acids, and glycerol. These are products of metabolic activity. That type of metabolic activity is known as catabolism, the breakdown of large molecules taken in as food into smaller molecules in the form of the glucose, amino acids, and fatty acids, and glycerol, which can be utilized by the body because the body cannot utilize carbohydrates, lipids in their form. So enzymes function to break them down to usable products. Enzymes generally accelerate reactions in the living system. A reaction that will have taken place in a very long period, in the presence of enzymes, it will take place in seconds. And enzymes are highly specific in their reactions. They catalyze substrates specifically. Even between substrates that look alike, an enzyme will be selective in going for its substrate. Enzymes are affected by extremes of temperature. We said enzymes are majorly proteins. And we know that proteins are susceptible to changes in their structure when they are exposed to extremes of temperature, whether low or high. Enzymes are also affected by extremes of pH because they are proteins, amino acids that have charges. When pH changes from one form to the other, enzymes are affected. They are also affected by extremes of ionic strength. These are some differences between enzymes and chemical catalysts. I mentioned before now that we have two forms of catalysts, two categories of catalysts. We have organic catalysts, where the enzymes fall into. We have inorganic catalysts. These are mainly elements that perform catalytic activities in inorganic reaction. So enzymes have higher reaction rates compared to chemical catalysts. An enzyme can have a turnover rate in millions per minute. So when carbohydrate is being metabolized in the system, whatever the volume of carbohydrate you take, it takes a minute quantity of enzyme to transform that large quantity into usable forms. And then enzymes operate under milder conditions. When temperatures are too high, the enzyme denatures. It loses its 3D structure, and so it cannot be active. When temperatures are also low, it also loses activity. So there is an optimum temperature within which an enzyme will operate and operate maximally. One other difference between them and the inorganic catalysts is that they have great specificity. Because of this specificity, like I mentioned before, they can distinguish between structurally similar metabolites because of their specificity. Enzymes of glucose metabolism will only catalyze glucose. Enzymes of galactose metabolism will only catalyze galactose, despite the fact that galactose and glucose, the difference in their structure lies in only one carbon atom. But this difference will still allow enzymes to distinguish between them. Enzymes have capacity for regulation. Enzymes do not operate without limit. It depends on the metabolic needs of the living system. When someone is hungry, the moment he takes food, the activity of enzymes will be elevated because they now have to break it down to satisfy your hunger. But when you are fed up, your stomach is full, your system is full, the activity of enzymes go down. Enzymes are organic in nature, catalysts are inorganic. Enzymes have active sites, catalysts do not have active sites. How do enzymes work? Because that was one of the questions we raised before in the introduction. Generally, enzymes accelerate reactions by lowering the free energy of activation. Every reaction that takes place, whether organic or inorganic, there is a component of the reaction that is referred to as activation energy. This energy is the minimum amount of energy every molecule in that reaction requires to get to the transition state, because every reaction goes through a transition state from which a product comes out. So all molecules in a reaction must acquire that energy to be able to get to the transition state and invariably get to the product. So this enzyme, what enzymes do is to lower this requirement. If the energy required was 50 joules, what the enzymes will do is to reduce that energy to 1 joule, for example, so that every molecule in the reaction vessel can acquire this 1 joule and get to the transition state and consequently get to the product. This figure on the screen, you have a reaction profile of a particular enzyme catalyzed reaction, and it is giving curves that represent uncatalyzed reaction and catalyzed reaction. The dotted lines are for catalyzed reaction, and you could see the arrow from the origin of the reaction, which is the substrate. The activation energy delta G naught has been reduced compared to the uncatalyzed reaction where the arrow has gone up. So we find that when it is catalyzed, the reacting molecules get to the transition state faster than the one that is uncatalyzed. There is an equation that gives free energy and rate constant, and that is represented on the slide. K equals to A E naught minus EA slash RT. The relationship here is when activation energy of a reaction is low, the rate constant will be high, and consequently the rate of the reaction will be high. So what enzymes do is to reduce the activation energy, which consequently elevates the rate constant. And so in the final analysis, the forward reaction is favored at equilibrium. Specificity of enzymes. We've mentioned that enzymes are very specific, and they have the tendency of being able to distinguish between closely related compounds because of that specificity. The active site is made in such a way that it only recognizes its substrate. And this specificity is determined by a component of kinetics that is referred to as Km, which is substrate affinity. Every substrate has a particular affinity for its enzyme, and every enzyme has affinity for its substrate. So when you mix substrates in the same vessel, the enzyme will specifically go for its substrate. It will not metabolize any other substrate. How can enzyme be so specific? Enzymologists put forward two theories to explain the specificity of enzyme. The first one is lock and key model. Lock and key model, the explanation is that for every key there is a lock, and for every lock there is a key. The key of a Mercedes car cannot ignite a Peugeot, and so also the key of a Peugeot car cannot ignite that of a Mercedes Benz. So based on this lock and key theory, they postulated that every enzyme fits into its substrate, just like a key fits into its own lock. But later on, enzymologists found that this had some defects, and so they put forward the induced fit model. And this provides a more accurate description. The induced fit favors formation of transition states. Remember that we have mentioned that for a substrate to get to product, it must go through a transition state. And so what the induced fit model puts forward is when the enzyme and the substrate come close, there's induction. Induction in either the structure of the substrate or the active site of the enzyme, so that they can fit into each other. So even if the substrate structure was not fitting for the enzyme, they are coming close together in the transition state will make an induced fit, so that the structures at this site are induced to fit into one another. And this is the more plausible theory that has been put forward to explain the specificity of enzymes for their substrate. The active site of a substrate of the enzyme has these features. First is a region within the enzyme, very minute region within the enzyme. You find that it is not the whole enzyme that participates in catalysis or enzyme reaction. There's a small portion, a microenvironment on the enzyme, which is very minute, that participates. So substrate binds to this small minute area, region of the enzyme using multiple weak reactions, interactions like electrostatic interaction, hydrogen bonding, and van der Waals forces, and in some cases, hydrophobic interaction. So specific binding of a substrate to an enzyme is dependent on arrangement of atoms in an active site. Enzyme activity is affected by some factors. We have mentioned some of them, but principally we have temperature. Temperature, every enzyme has an optimum temperature of activity. Extremes of temperature beyond or above this optimum temperature will denature the enzyme and make it inactive. pH, hydrogen ion concentration of a medium. Because enzymes are made up of amino acids, we have acidic amino acids, we have basic amino acids, and we have neutral amino acids. And some of these are present in the active site of enzymes. So they operate at particular pH. Acidic amino acids, they have functional groups that have negative charges. So if they are present in the active site and you change the pH to positive positivity, towards positivity, they will lose activity. Because instead of being negative, introduction of hydrogen ions will make them to be neutral, and so the activity of the enzyme will be lost. Substrate concentration. We said enzymes act on substrate. If you don't provide substrate for the enzyme, it will not be active. And the higher the concentration of this substrate, the higher the rate of the reaction. It's a direct proportionality. Another factor is enzyme concentration. When you increase enzyme concentration, you speed up the reaction, because the presence of more enzymes provide more active sites for which the substrate can bind. Another factor, we have activators and inhibitors. Enzymes are susceptible to effect from either activators or inhibitors. Activators are those substances, when introduced into an enzyme system, will make it act faster, while inhibitors are those that retard or slow down the activity of an enzyme. And lastly, on these factors, accumulation of end products. When products accumulate beyond the need of the cell, there is a tendency for the product to inhibit the enzyme activity. This is referred to as end products inhibition of enzyme activity, because the cell is very economical. When it requires a product, whatever the importance of that product, there is a threshold the concentration gets to, and then that product will now, through feedback inhibition, tell the enzyme, no, there's enough in the cell, don't produce more. This also is one of those effects on enzymes. Furthermore, we could use this to demonstrate how enzymes are affected by pH. When we are talking of optimal pH of activity, we have a particular enzyme in our stomach. Our stomach operates in the acidic medium. The pH is less than 2, so that it's very acidic. And this enzyme pepsin acts on proteins, and it is in the stomach. We also have amylase in the saliva. Our saliva has an optimum temperature, this enzyme operates at 6.8. 6.8 is close to alkaline pH. If pepsin was to be taken out of the stomach and put in the mouth, it will be inactive, because its pH, that pH change will affect its activity. So also, if amylase was to be in the stomach, it will not be active, because that pH of the stomach, which is less than 2, will make it inactive. This is a graph showing that every enzyme has its maximum optimum pH. And so at lower pH, you see that the enzyme activity is low. As you increase the pH, it's rising. When it gets to the optimum pH, the activity is maximum. Then as you go further with increase in pH, the activity continues to decrease. The same thing with temperature. It also, every enzyme in the living system has an optimum temperature of activity. Below or above this temperature, the enzyme will lose activity. This is also demonstrated with this graph. At low temperature, the activity will be rising until it gets to an optimum point where the activity will be maximum. Beyond that temperature optimum, the activity will go down. There are other factors that may influence enzyme activity: genetic control, covalent modification, allostatic effectors, zymogen and isozymes. Basically, enzymes are synthesized in the living system when the substrate to act upon is available. This is subject to genetic control. If there is no substrate for an enzyme, it will not be expressed. Covalent modification depends on if one is fed up, that is, you have taken enough food, enzymes that are related to activity on that food will be active. If you go into a starving state, when you are now hungry, they are deactivated. So other enzymes that will act to provide you with the fuel you need in your system will come up. This is what is referred to as covalent modification. Examples of this It's only in your 400 level you come to know about glycogen phosphorylase that will act on glycogen in the liver. When you are hungry, it will act on glycogen in the liver in the active form. But when you are fed, you have enough, that glycogen phosphorylase will be deactivated because you don't need the store to release whatever it has. You have enough in the blood. But when the glucose in the blood goes down, that enzyme will be activated to release glucose from the glycogen store. Allosteric inhibitors, like we have mentioned, that every cell has a threshold for the need of any product. Once that threshold is attained, that product will feed back through inhibition to regulate the enzyme that produces it. Zymogens and isozymes. Zymogens are enzymes, are proenzymes. They exist in inactive form. When the product or the substrate they are going to act upon is in the system, they are activated by processes of cleavages of some amino acids. Next, we have classification of enzymes. There are 1001 enzymes in existence. In 1961, the International Union of Biochemists came together to say this array of enzymes, there is need to classify them so that enzymologists and scientists in the future will be guided to know this particular enzyme that is acting this way, it belongs to this class. So from that conference of International Union of Biochemists, they arrived at 6 classes of enzymes, although there is a 7th class that has been added, but we restrict ourselves to the traditional 6 classes. These classes, we have oxidoreductases. From the name, oxidation reduction. These are enzymes that catalyze reactions involving oxidation and reductions. And we have a lot of them, a lot of examples in the living system. In cellular respiration, photosynthesis, you see enzymes that are either involved in oxidation or reduction. So any enzyme that is involved in this type of reaction is categorized as an oxidoreductase. We have subclasses, we're not going into that now. Second class are transferases. From the name, they transfer functional groups from one reactant or one molecule to another. We have metal transferases, we have amino transferases, we have phosphotransferases. All enzymes that transfer one molecule to another, they fall into this category of transferases. And then we have hydrolysis. From the word hydrolysis. So enzymes that hydrolyze, they use water to break down molecules through hydrolysis, through cleaving of chemical bonds. They are classified as hydrolysis. Virtually all digestive enzymes belong to this, like amylase that act on starch, protease that act on proteins, lipase that act on lipids. They all fall into the category of hydrolysis because they hydrolyze macromolecules to micromolecules. The 4th class are the lyases, also derived from lysis. When they add or remove atoms to or from a molecule, they form or break a double bond. So when they add to a molecule, they break a double bond. When they remove an atom from a molecule, they create a double bond. So lyases are generally enzymes that create double bonds or break double bonds into single bonds. The 5th class are isomerases. Isomerases, you must have heard of isomerism. These are compounds that exist in multiple forms. They are the same molecules, but structurally they look different. So what isomerases do is to rearrange atoms within a molecule to give rise to its isomer. So any enzyme that does this is categorized as an isomerase. We have many examples under this. We have epimerases, we have isomerases, we have stereoisomerases and all that. The 6th class are the ligases. From the name ligation, ligation means joining together. So all enzymes are joined twin molecules together. And in most cases, they use energy to join these 2 molecules together and categorized as ligases. And one prominent example we have in biochemistry is DNA ligase. DNA ligase joins DNA fragments together through formation of bonds. So these categories or classes are further subdivided into subclasses, like I mentioned. Every class has a subclass, and every subclass has a subclass, to which result a 4-part enzyme commission number. Every enzyme you see has 4 digits representing class, subclass, and subclass. And one example we can cite here is alcohol dehydrogenase. It has EC1111, where 1 is standing for the class, 2 the subclass, 3 the subclass, and the last digit is the listing of the enzyme on the enzyme commission list. So this is a table showing the summary of the classes we mentioned, 1 to 6, and the type of reaction they catalyze. An example is given, and a reference book is cited below, where you can go to the chapters that discuss fully about these classes of enzymes. And then nomenclature of enzymes, like I mentioned, is based on the enzyme commission nomenclature. The last bullet you see here is EC1111, which I mentioned, which stands for alcohol dehydrogenase. Alcohol dehydrogenase is an oxidoreductase. It acts on alcohol, ethanol, and it breaks ethanol into aldehyde, acetaldehyde to be specific. And so because it is the first enzyme, it has the 4th digits as 1. And under the subclass, it is also the first enzyme. That is why it has the next digits as 1. And then the subclass is the first. That is why it has 1. And in the list of all enzymes in nature, alcohol dehydrogenase is number 1 on the list. And then we have other systems of nomenclature. We have systemic names, apart from the EC, like when you see L-alanine 2-oxoglutarate aminotransferase. What it indicates is that this enzyme transfers amino group. And it is transferring the amino group from L-alanine to ketoglutarate at position 2. So when you see L-alanine 2-oxoglutarate aminotransferase, it tells you from the aminotransferase it belongs to class 2, and then from the name it is transferring an amino group from L-alanine to oxoglutarate, and the position of transfer is on carbon 2. We also have common names. Common names are usually derived from the name of the substrate, and ASE is added to give it the connotation of an enzyme or nomenclature of an enzyme. Urease, for example. Urease catalyzes hydrolysis of urea. Urea is the substrate, and the name is now derived from that substrate, and the enzyme is called urease. Lactate dehydrogenase, it catalyzes the removal of hydrogen from lactate. So lactate is there, indicating that lactate is the substrate. Then dehydrogenase is removing hydrogen from lactate and transferring it to pyruvate. Glucose oxidase, from the name, glucose is being oxidized, and the enzyme that is oxidizing it is an oxidase. Thermodynamic properties of reactions. We have an equation that is referred to as thermodynamic equation. We have delta G equals delta H minus T delta S. Delta G is our activation energy, or gives free energy. Delta H is change in heat formation or enthalpy. T is temperature. Delta S is entropy. That is the degree of disorderliness. So this equation describes how a reaction will proceed. If delta G is negative, then the reaction will be spontaneous and hexagonic. Spontaneous in the sense that it can operate without being triggered, and it's hexagonic because it will release energy. But if delta G is 0, the reaction is at equilibrium. If delta G is positive, that means no reaction is going to take place until energy is provided. For example, we mentioned when we were talking about ligase, the joining of molecules together through the formation of a chemical bond must be done in the presence of ATP energy. That reaction can be classified as endergonic, because energy must be provided. If energy is not provided, there will be no reaction. So delta G in that type of reaction is positive. So this equation tells us the possibility of a reaction taking place or not taking place. Thank you very much for listening, and I hope when we meet to interact, more explanations will be offered on this course. Thank you very much.